All right, next we're dealing with moles and molar mass, and this is really a fairly easy concept, especially if you have a good handle on doing dimensional analysis like we went through in the last chapter. And if you have a handle on this, again, most of the semester becomes much easier. If you pay attention to units, understand what the units mean, and try to visualize what we're doing when we convert, just instead of memorizing, go through step A, B, C, D, understand the concepts, will just make life a lot better for you. So a mole itself, it is just a number. Keep that in mind. Like a dozen means 12. A mole of particles means 6.022 times 10 to the 23rd particles. Doesn't say what the particles are, we have to specify that, but a mole is just a number. It represents a very big number, and we use it because it makes it easy when dealing with very, very large values and dealing with very, very small atoms, because even a drop of water has a tremendous amount of atoms in it, so it makes it simpler for us. I've seen texts, I've seen professors describe moles, tell students that moles tells you how many atoms you have. I've seen professors tell students moles tells you molecules. Well, that they can, but that's not what they mean. A mole is still just a number. And if you keep that in mind, then you understand the concept better, to make it a lot easier for you. Now, again, it helps, I think, to keep in mind where a mole comes from. If you have 1 gram of hydrogen atoms, you'll have very, very close to a mole of hydrogen atoms. Not exact, because we actually made the definition using, as this shows, using 12 grams of carbon-12 instead of 1 gram of H1. It's almost the same, give you almost the same number, but we did this just because it's easier to isolate 12 grams of carbon, because hydrogen is a gas room temperature, so measuring a precise mass is harder. So it's just easier to use the carbon. So that's what we use as our defining value to decide how much, what quantity a mole really is. So it just compares or converts the number to something we can measure on the scales. It converts, the mass here to a mole, which is really just a way of describing numbers. Instead of 1,000 or a billion, we just use a mole of something. Again, we use this because atoms and molecules are so small, we use so many of them at a time, even with 1 drop of reactant. It just makes it much easier than using the actual number itself. This shows basis of conversions. I think, again, with conversion factors, it's good to keep in mind that the quality this starts with is 1 mole equals 6.022, but let me do this, 10 to the 23rd. That's where it comes from, and that's what this relates to, but I don't like the way they did this. I think this is very poor units, because number of particles, this should say 1 mole of particles. If I can write here. And this should say number of moles of the particles. This is where people get tripped up all the time in moles, because texts are not very careful on their units. I know I can't write that very well, it's kind of sloppy over here, but anyway. But all of these should say not just a mole. Down here, this means nothing unless I say a mole of something. So when I have up here, or when they wrote up, this is from the text, they wrote up here 6 times 10 to the 23rd particles, this should also say 1 mole of particles. Saying a mole is completely meaningless. So this is what leads to confusion when people deal with moles. So be careful about this, and always have a mole of something. And even this is horrible. Number of moles means absolutely nothing unless you say moles of something. It's like saying I've got 12,000. Well, 12,000 what? Unless I tell you 12,000 of something, you have no idea what I'm talking about. Same thing with moles. I've got to say moles of something, not just I've got moles. So be careful about that. This is an example from a different text I've used, and I've used this example a lot because it again shows how moles can be described incorrectly. And this is pretty bad in my opinion, but other than that, it's a decent text. I just think this leads to confusion. This is what it states. 2 gloves is a pair. 12 rolls is a dozen. 144 pencils is a gross. 500 sheets of paper is a ream. 6 times 10 to the 23rd atoms is a mole. Well, actually, all these are incorrect except for this one. This is the only relationship they have that's correct. That's just because 1 ream is only used to describe paper. But these other relationships, these are not equal, because 1 glove isn't a pair. 1 glove is a pair of gloves. So that's what it should state to be proper. 12 rolls isn't a dozen. 12 rolls is a dozen rolls. I know that sounds nitpicking, but this is what makes moles a lot easier for you if you understand what the units mean. Saying 144 pencils is a gross, again, is incorrect. What it should state is this. This is the correct way of describing these units. 2 gloves is 1 pair of gloves. 12 rolls is a dozen rolls. You've got to have the rolls along with that dozen, not just a dozen. 144 pencils is a gross of pencils. Again, those are very critical. Again, paper, the ream of paper, is, in that case, is redundant because ream is only used to describe paper. That's implied in that definition of quantity. But with moles, this is critical. 6 times 10 to the 23rd iron atoms is 1 mole of iron atoms. You have to say mole of something. You can't just say a mole. That's completely meaningless. And if the text does this, if I do this, yell at me. I've caught myself, I've done it on Blackboard and caught myself being a little casual about that. Quite often it's implied what we mean. And I think a lot of professors, we use it so much we get careless sometimes. And if you notice this in a problem in the text, please let me know. I try to catch those when I see them where they say, how many moles are in 10 grams of water? Well, again, that means nothing unless you specify moles of something. So watch out for that. And this is the main thing to keep in mind with moles. That makes moles much, much easier to deal with. So to convert between moles and numbers, here are a few examples. I'll work some more out in a little bit, but that by hand, was I kind of like working by hand. I think it's easier for you to see them versus just on PowerPoint. So same thing. We start with so many atoms. We have our units here. Atoms. We want to put atoms on the bottom to cancel out. Up here we have 1 mole of atoms, which is the unit we're left with. We're left with moles of atoms, not just moles. So these are units we're trying to get to. And so up here we have 1 mole equals 6 times 10 to the 23rd. So in this case, a mole of atoms is 6 times 10 to the 23rd atoms. Sorry, backtracks again. Going the opposite direction, it's the same thing. We have moles of atoms up here. So we put moles of atoms on the bottom so they cancel out, and we've got atoms for our final answer. So it's the same process. You notice here, it doesn't matter what atoms I have. It's still, whether it's helium atoms or lithium or sodium or uranium, it's still the exact same calculation because we're just counting numbers. We don't care about how heavy it is, how many neutrons are in it, how many electrons it has. It's just numbers of atoms. So it's nice and simple. And it's the same thing if we were dealing with molecules. So here, we have 1.5 molecules. So now instead of having moles of atoms to atoms, we have moles of molecules to molecules. Again, this is our conversion factor. 6.022 times 10 to the 23rd is a mole. It's like we went from milli, the metric prefix means 10 to the minus 3. We're doing the same thing here. Like I said, if we went from 1 millimeter to 10 to the minus 3 meters, well, again, this is our real conversion factor, and that's all we're doing with moles. It's the same process. It's like a mole is a prefix, and we're replacing that prefix with the number it represents. And that's it. That's all we're doing with moles. Here I had moles of molecules. Again, it doesn't matter what molecule I have, whether it's water or carbon dioxide or sugar or acetaminophen, whatever it is, it's the exact same calculation because I'm just dealing with numbers. Again, that's what a mole is telling me. It's just a shorthand for a very large number. Opposite direction, same thing. Mole of water, I put mole of water on the bottom and water molecules on the top to get my final answer in molecules themselves. Here, just to point out, I put this in parentheses because in many cases molecules is just implied. We put water since we have the formula. We don't need to say molecules, but you can put that in there, but it's kind of implied. Same thing with atoms. Sometimes we'll say atoms. Sometimes if you put the formula down, you don't need to say it's just to clarify that there are atoms we're talking about. So just another example on the bottom, sort of the same thing. Now, of course, when dealing with, well, I'll go through some more examples of a few calculations of moles to numbers in a few minutes. Let me finish this up here first and discuss moles to mass, because again, chemical reactions care about numbers of atoms and numbers of molecules and numbers of formula units for compounds. They don't care about the masses. H1 isotopes versus H2 versus H3. H3 has 3 times the mass of H1, but chemically they react the same way. So chemical reactions don't care about the masses really, they just care about how many atoms you have. But we can't count atoms on the scales in labs, we can measure mass though. So we need a way to convert the mass we measure in lab to numbers that reactions care about. So that's what we need the molar mass for. Molar mass is the mass in grams of 1 mole of whatever substance we're talking about, whether it's an atom, a molecule, or a formula unit. Molar mass for helium, for example, abbreviated as capital script M, is 4.003 grams per mole. And we actually get this from the periodic table. In fact, the average mass we discussed that's on the periodic table, it gives us the mass in 1 AMU of 1 atom of the element. So 1 atom of helium has a mass of 4.003 AMU. But it also gives us the mass in grams of 1 mole of that element. So 1 mole of helium atoms has a mass of 4.003 grams. So the molar mass of helium is 4.003 grams per mole. So that's it. So we can use the periodic table to tell us the mass of 1 atom, or also the mass of 1 mole of those atoms. So therefore we can use this to convert between mass and numbers. So to find the moles of hydrogen atoms in 1 gram of hydrogen, we just start with the gram of hydrogen. Look at your periodic table, and it says below the hydrogen 1.01, which again that means 1.01 AMUs per atom, or it means 1.01 grams per mole. So again, that's what we're doing here. This is our conversion factor that we get from the periodic table, 1.01 grams for every 1 mole. And this is talking about hydrogen atoms, so we have 1 mole of hydrogen in this case. For 12.5 grams of hydrogen, it's the same thing. When I'm getting 12.4 moles of hydrogen, so simple enough. Or to find the mass of 2.5 moles of helium, well, now we have 2.5 moles of helium. Of course, we need to put moles of helium on the bottom to cancel out. Now we have grams of helium on the top. Look at your periodic table, and it tells you there's 4.01 grams per mole for helium. So you get just 2 sig figs, 10 grams of helium. Or 2.5 moles of lead, we do the exact same thing, but for lead is 207 grams per mole. So we get a mass of 518 grams. And I think this is good to point out. For these 2 examples, we have the exact same numbers of atoms. 2.5 moles is still counting how many atoms we have. It's just talking about moles of atoms. But this lead, same number of atoms, but the lead weighs 50 times more. So much heavier atoms, even though we have the same number, have a large difference in mass itself. For compounds, on the other hand, we need to add up the individual atoms in a formula unit or in a molecule. So we sum all those up, add them together, and that gives us our actual mass of the molecule, which also gives us the molar mass of the molecule. So for carbon dioxide, for example, we have 1 carbon atom, we have 2 oxygen atoms. So look up in the periodic table, 1 carbon atom has a mass of 12 AMUs, or 12.01. Oxygen atoms, 16.00 AMUs each. Add those up, and you get 44.01 AMUs per molecule. But this also gives us 44.01 grams per mole. So we can use this to convert between mass and moles for a compound. Just a subtle difference here. Molecular mass versus formula mass. Molecular mass is only for molecules that are chemically bonded together to form one cohesive unit. Formula mass, something like sodium chloride, which we mentioned, is really just bunches of ions stacked together. It's usually described as, well, formula mass is for any formula, whether it's molecular formula or ionic formula. More generic term. So just be careful about wording there. Again, ionic compounds versus molecular, we'll describe those a bit better in a few chapters so you understand them a little bit better. So then for carbon dioxide, we just figured out its molecular mass, which is the same as its molar mass. So we can figure out the mass of 1.5 moles of CO2. We do the same thing. 1.5 moles. We just calculated 44.01 grams per mole for CO2, and we get 66.2 grams. We're going the opposite direction to find the moles of molecules in 85 grams of CO2. 85 grams. Now we have 1 mole for every 44.01 grams, so that these will cancel with grams. And you get 1.93 moles of CO2. This is where I've been careless about it, and text can be very careless about it in saying moles. You'll often see, find the moles in 85 grams of CO2. Well, you can't do that. I need to say moles of something, because in CO2 I can have moles of atoms, I can have moles of electrons, moles of protons, moles of neutrons, moles of all sorts of things. So I can't just say find the moles in 85 grams of CO2. I've got to say find the moles of molecules or moles of something else. I left this in here. It's from the text, and I think this is kind of ridiculous. This goes against dimensional analysis. It makes it really hard. Trying to memorize this will give you a headache. I recommend it's not worth the effort. If you pay attention to units, understand the 2 conversions we've gone through, the 2 basic conversions, then there's nothing else to memorize. And if you understand them, then all this junk here you can ignore. First of all, people that try to memorize this, again, get it wrong at least half the time, because they're trying to memorize something and don't understand it, and there's too many things here to memorize, going 2 different directions. It just causes all sorts of confusion, and that's one thing I didn't like about this text, but can't really change it right now. But again, things like this happen in most texts I've read, so I can't say this is any worse than other texts. I just really don't like this type of conversion because it causes headaches for you guys, and rather make it simpler. And this is, well, if it's done correctly, this is from another text. I like this way of looking at doing conversions. There are only 2 things to remember. It's where to get your conversion factors. If you know how to deal with dimensional analysis, you want to cancel units out, you only need 2 real conversion factors. For one, I'll come back there. To go between mass and moles, we use the molar mass from the periodic table. That's it. If you know the periodic table gives you the grams per mole, then that's your conversion factor. Make sure the units cancel out, and you're done. No need to worry about memorizing all the other junk. To go between moles and numbers, use Avogadro's number. 1 mole is 6 times 10 to the 23rd. Let me write it equals, sorry. It really doesn't like it when I try to write decimals. I'll just do 2 sig figs here. Make it a little quicker for you. Sorry, it should be 3. 6.022 times 10 to the 23rd. These are your 2 conversion factors. You know these, and you know you need to cancel units out. That's all you need to do. All this junk is just going to give you a headache and cause you to make careless mistakes probably at least half the time. Maybe more than that, or in most cases more than that. Again, this is part of this I X'd out. This is from a text, and this is again an example where they say you go from moles to molecules, and that's not always the case. You can go from moles to numbers of atoms, to electrons, to protons, all sorts of things. So it's just moles to numbers. That's the thing to keep in mind. So a mole is just a shorthand for a very large number. And that's it.